All right, you guys can hear me. No response, but I guess it's okay.
I can hear you.
Oh, good. Right. Thanks. Right. So, yeah, this paper is kind of pretty deep. There's a lot of things in here. So, hey, anyway, so we have to kind of weed through it. So I guess the best place to start, I put a book up here. It's called The Quasi-Elastic Neutron Scattering. That might be a good place to begin. And then of that book, I put some page numbers to go to because it's a long book and it's got some sections that seem to be more than what we're kind of dealing with. Like the first part of that book is just physics of neutrons and stuff, and it's like too far off track, I guess. Well, then I'm saying 124. Although it does show it's 1987 or something, so it's an old book. But it's when they first developed quasi-elastic neutron scattering at Grenoble, France. So he was at some school near there and kind of wrote a book about what was going on. And in the beginning, it was just crystals. So they looked at things like atoms in a crystal and how they move around. You know, so you can get the diffusion of the motion of the atoms with this technique. So a lot of the stuff is based, like begins with that. So this idea of jump diffusion is like one of the things that they talk about. So basically, if you're in a crystal and then you have an atom that's diffusing through the crystal, like a gas atom, particularly the neutron is useful with hydrogen. So you can tag like hydrogen, deuterium. The deuterium makes the, in terms of the dynamics, it makes it disappear. So you can just see the hydrogen. So you have like a polymer membrane. It's going to have water in it. So it's reverse osmosis. You want to push the water through it. You know, so you want to look at how the water moves from the membrane. The membrane's full of hydrogen, right? So the polyamide membrane. So it's made up of these two. So it's just like this nylon rope trick thing I mentioned before. You have like a water soluble and a like cyclohexane soluble. So this thing would be water soluble. Like if it isn't chlorine, it would be OH. So that'd be a carboxylic acid. So you stuff a chlorine instead of an OH on it, and that'll react with a hydrogen to make HCl. So it's a condensation reaction, and that polymerizes. And you see it's trifunctional, so it's going to make a network. If it was bifunctional as a normal nylon, and that makes like linear nylon, like nylon 612 would be 6 carbons in one of them and 12 in the other. So that's one of the two components. He called it TMC, I think. He uses a lot of acronyms in here, so that's pretty painful if you don't know the acronyms. So TMC is one of the acronyms, and the other ones are TMS, I guess, because that's called I don't know what it's called. What's it called? Whoops, that was the wrong way. That's called TMS, trimethyl chloride, right? Even though it's called benzyl carbonyl, whatever. So he calls it TMS in there. And the other one is MPD, which is just the same thing like an aromatic, but it's two amine groups on it, right? And then that'll be like a linear, so that's a linear chunk. So this aromatic group can spin around. Someone's got a relaxation in the network. So the protons that are stuck to that are going to have this rotational dynamics to them. And the other protons are, I don't know, they're kind of fixed, I guess. They have vibrational, but not this rotational thing. So anyway, he makes that's what the network's made from. This one will dissolve in oil. So you have like hexane, cyclohexane, and then you have water in the other one. And then if you put the two together, if oil and water don't mix at the interface, these things meet and condense and produce hydrochloric acid. So if you can soak a paper substrate with water and then put this organic thing on top, right at the interface, will make 100 nanometer thick polymer, kind of solid polymer film. Well, the structure of that film, so there's quite a bit of papers on this thing, like the structure of the water. So the structure, let's see, no, that's a water structure. Wait, heterogeneity of polyamide films. So it's the same kind of film. This is 2003 from Israel. So Israel is like serious in the reverse osmosis because they don't have any water, and they got a ton of money. So like that's where all the drip irrigation, reverse osmosis, everything to do with like making water from ocean water. That's Israel Central, right? So anyway, that's their gift to the world here. So anyway, so these membranes, like these are, so polysulfone's this tough temperature insensitive industrial polymer that you can hit with a hammer and nothing happens to it, like the prison plates, polysulfone. Can't make a knife out of them because you can't break it. So polysulfone, and then you can put a layer of this polyamide interfacial polymerize onto the surface, and you make this separation. So that if you make porous polysulfone, then the stuff flows right through it. Then this amide, this 100 nanometer polyamide layer is a transport layer. That's where you're trying to do your separation from. And then you have this really tough polymer to hold it. So they show that there's like, I mean, there's not much you can say, but basically it's not clean, right? There's a lot of, you could say aggregates, and then there's pores, and see, I mean, there's different things. He's looking just at that black layer, the polysulfone's down here. The polysulfone, the water just goes straight through, right? It's 50 nanometer, but still the water can go through that thing, right? So this is a really thin layer, separation layer, and you can see clusters and different stuff in there, right? So our guy looks at that and says, this is where he's showing that rotation of that one aromatic group, and then he shows this thing, which you can't really blow up enough to see. Maybe you can blow it up more here. See if I can keep blowing it up. You can't really see when you just look at it what he's showing. He's got regions. He's saying that there's clusters. There's aggregates of the, and you can see here's some aromatic rings. This is on a molecular scale. This is 10 nanometer. That's his separation there. It would be like 50 nanometer. And then he's got regions where it can fill up with water. Water is like a couple angstrom. So this is 10 angstrom. So 1 nanometer. So you can pack a bunch of waters in there. So that's going to be like a local bulk water transport going on. And then the water can have this like tortuous, like a diffusion pathway, have a worm-like pathway. And then you can have this translation, which is this jump diffusion. So you have the water sticks around for a while and then pops. So you have a frequency of that. There's a tau associated with that popping, like how often does it pop? And there's a distance L, the pop distance. This comes directly from crystal quasi-elastic neutron studies of this transport through crystals. We actually have free volume and things can pop through. And there's a certain frequency of the popping depending on the temperature. And then there's a distance of the popping. And you can measure those two things with the quasi-elastic neutron. So he's saying he has this mess of different transport things going on. And all right, so and also it's made of hydrogen, so there's this flipping of the aromatic ring thing going on. So you have so first thing, he takes the polymer dry and he measures the dynamics of the polymer film. So he can get the polymer hydrogen motions, because you can't pull the hydrogen off the polymer. You could, but it would be difficult. Like you'd have to have a chemist make the hydrogenous meso chloride thing and then make the diamine thing. it could be done pretty easily, like, because you can buy deuterated benzene, and they're both just derivatives of deuterated benzene. So actually, you could make the deuterated polyamide, but it would cost you about, like, probably something like $50,000 a gram to do a custom synthesis like that, or you could get a grad student to do it, and it would still cost you $50,000, maybe 100, maybe 200, because it depends. It's 7 years, it's like time goes by, So basically, it's cheaper to just take the commercial material, and then you aren't sure it's really going to be the same. But so anyway, what he does is he uses that as like a background, so he gets the dynamics of the film dry. And then other people have measured this. So there's hundreds of papers in this topic, just this transport kinetics thing of this particular kind of reverse osmosis membrane. So you can see, like, there's a lot of money in it. So basically, it's kind of a deep subject into one narrow area of a field that's got a bunch of other things. So the field of membranes already is an isolated little thing. You take the polyamide supported heterogeneous membranes like this. So that's another little area. So, but basically, there's probably thousands of people working on this in the world, maybe 5,000. Right. And of those people, the papers are all getting published in Nature and like Proceeds National Academy in Science and Advanced Materials and stuff. So it's important, and people can see it's important if they want to have drinking water, I guess, So that justifies delving deeper and deeper into this subject area. Right. So it's kind of, anyway, so that's kind of what he's doing. In the end, he measures the diffusion, this popping time, so the time it resides and then pops, like this DTR thing. So that's the tau. And he can measure, he has two instruments. He's got a BS instrument, which is kind of an odd acronym. That's the backscatter, which is that's at long times. And then he's got a time of flight instrument, which is at shorter times. So he's got two taus here. This is picoseconds. I think that's the TOF, and the backscatters nanoseconds, right? So they're on two different time scales, the two machines. They both seem to work the same way. So you tag the neutrons coming in, and you have a way to separate the energies of the neutrons. I guess by the time they pass through, the higher energy ones pass through faster. So you can have a chopper, like a tube that spins at a certain speed, and it only allows, like, say you had two windows like that and it spun around. So the time, if it's coming straight through, it can pass that window. And if this window swings over, then it can pass straight through. So depending on the speed of the chopper, you can select the velocity of the thing going through, which is the energy, right? So if you set the one chopper in front, your sample, and another chopper in back, and then do a normal neutron scattering measurement, which is like collect at the angle, then you can get a time dependence to like how much energy was transferred in the process. The two things are chopping at the same speed, then you get the elastic. So the delta E is 0. And then if you change the speed of one of them, you can get a delta E that's plus or minus, usually minus. So this thing's going to absorb the energy. And then from that energy difference, you can get the size scale associated with that energy transfer in the material. That's kind of roughly the idea of what's going on here. So he's got two. So if you take and then you can scan across energy, but change on the speed of one of the choppers. The choppers isn't actually two things. It's actually a tube that's curved that goes through. Right. So it's got more than one tube on the blades that spin around. So it's kind of a complicated little machine. That's roughly the idea of it. So you can pick out the different energies. So the first thing he shows is this this thing that he calls a IFWS, which is the cheat sheet on this stuff. Yeah. It's an inelastic IFWS. Fixed window scan. Yes. So the fixed window scan is the idea. You got to look at one energy gap of the thing. So there's an elastic when the delta E is 0, and there's an inelastic when the delta E is some number, right? And here is fixed window. Delta E is given someplace, and it's 2 micro electron volts energy difference. So by the speed of the neutrons, 1/2 mv squared for the neutron flying through, that's the energy. So that comes out to be micro electron volts. So whatever the voltage to the energy associated with an electron at certain voltage is microvolts. I mean, anyway, that's how it works out. So it's that amount of energy, and he scans all different energies here in the end. I mean, he's going to be doing energy scans. So he's going to have, like here, it's delta E micro electron volts, and one's for the time of flight, which is a small numbers, and one's a backscatter, which is large numbers. So he can measure different dynamics with the two instruments. This is 45 micro, that's 1 micro electron volt. Right? So anyway, so that's the idea. So when you do that, if you look at the elastic peak at 1Q, so you do a scan across Q, you get the scattering function, which is going to be some decay function. And then if you fix it 1Q, when inner delta E is 0, you get the elastic, which is a spike, right? And if you look at it, it'll decay down. So it's absorbing energy as it decays down. There's some instrumental broadening. So there's some breadth to the, it should be a delta function if delta E is 0, but maybe the two things aren't lined up exactly right. And something about the spinning and the, whatever happens, but it broadens out for whatever reason, right? So the spike is actually a Gaussian, right? So it's like a e to the minus q squared, e to the minus e squared, I get, or e, this is something, whatever. It's a Gaussian peak, right? So it's a bell-shaped curve. And then underneath that is a Lorentzian. So that a Lorentzian is like a Gaussian, except the peak is lower and it's broader. So it's got higher tails on it. So Lorentzian is this function. You can get it from the ratio to Gaussians. You can also get it just from the transform. So this is the Lorentzian function. It doesn't look anything like a Gaussian function. Like Gaussian would be e to the minus omega squared. And this is but if you think about it, e to the minus omega squared would be 1. So 1 over 1 plus omega squared plus omega 4 divided by 4 divided by 2 factorial, etc. Right? It'd be a power series. And the first term of the power series is that. So this is like the first term of an exponential, if you think of it that way. Another way to do it, to get this Lorentzian, is there's 3 ways to do it. One is that power series thing. I invented that way. So that's not the textbook way. The mathematical way to get that is to say it's a ratio of 2 Gaussians. And if you take the cumulative distribution function, which is an integral of the Gaussian, right? And then that would start at 0 and increase. So the Gaussian's bell-shaped. You integrate it from like 0, so it's 0, and then it increases, and then it plateaus out when you get to the tail part, right? So it's a cumulative distribution function. So the derivative of the cumulative distribution function is the distribution function. So if you take the ratio of 2 cumulative integrations of a Gaussian, and then the exponential arguments add or something, and then you take the derivative of that thing that you get out of that, you'll get this function, because this will come out as a prefactor of it. Or you could take, another way to do it is how we did it before so this is the same thing as the Maxwell equation, like for the frequency dependent Maxwell equation, which relates back to exponential e to the minus t tau, or t over tau. We did a Fourier transform of that, and we got this. So you can Fourier transform e to the minus t over tau, and get this directly out as a prefactor, because the exponential at minus infinity is 0, and at 0 is 1. So the exponential term drops out, and you just have the prefactor left, which is this thing, right? So there's 3 ways to get this function. And generally it's just kind of, just taken that anyway, you need that, because that's what the whole game here in the quasi-elastic neutron is, that function, that Lorentzian function. It's got another name too. It's Lorentzian or Cauchy function. So that this gamma is the half width of the peak, and that's used to get the diffusion coefficient. So so if you look at the curves, so it's going to be a Gaussian, so the bell-shaped curve in the middle, and then this broader shape Lorentzian, right? And then from that's where you're going to get your time. This is just the elastic part, the thing in the middle. delta E0. Right, and then you can get, that can be made up of multiple relaxations. So this thing can turn into a summation of these terms. Right, so he does that somewhere here. He's going to make that into a summation of those terms and with specific features. So you can see there's the W1 and the trans TR1, and then there's the, so it's all a bunch of those. In the end, this would be like a summation of a bunch of those. Like you go back to that book. So he shows the chopper in here. The first part is like crazy neutron stuff. And then let's see, where's my page? Here. The pages I want to go to are classical neutron 124. Let me just go to 124. Going near that. This is a pretty involved paper. So the first chapter, like a lot of these books, the first chapter is not the one you want to look at. He shows the choppers here and stuff. Even in 1987, I think, 88. So they already had all the equipment. You know, what they didn't have was a super powerful neutron beam, because these are subtle differences of things, you know. So basically now they have flux that'll like huge flux of anyway, that's the Gaussian. So the one relaxation is a Gaussian, the bulk transport term is a Gaussian, and then the others are these Lorentzians, and then he goes through it in here. I mean, there's a lot of math, but basically if you start on 124, you can kind of marginally understand and keep looking for this Lorentzian, because whenever that shows up, you kind of feel comfortable, because you should feel somewhat comfortable. And then that's 147, 153. Let me just skip through where I've had warmed feelings about this book. Anyway, this, I guess, is the Bible of this field, you know, so you might want to take a look at it if you're doing this. And if you want to understand the paper marginally, you might want to just glance at the pages I mentioned in here, because it'll at least make you feel like it's something that somebody's doing. I mean, that's the Lorentzian thing. Oh, this is where he shows how you get, well, he just shows this is a time-dependent one, and then he transforms it and gets he doesn't show the transform, but he basically, this is like what we did before. In other words, a relaxation time, T divided by the relaxation time. That's just an exponential decay for the intensity as a function of time. If you transform that, so that's transforming Fourier transform, that times I, e to the minus I omega t, integrate that from 0 to infinity, you'll get this function out of it. Okay, so that's how those, this one you should recognize as just exponential decay, Maxwell model, right? So it's got an elastic and a viscous. So everything behaves that way. And then the other one looks foreign, but it's basically the Maxwell transform, and that's also the Lorentzian, right? So he shows like how that, I don't know, he shows how that behaves for argon, and these are all like simple kind of systems here. So there's 153, and then chapter 5, I guess the whole chapter. So he goes, I mean, if you skip along and get to the parts that seem to be relevant, oh, this is chapter 5, I guess. So the whole chapter 5, which is just in these crystals, like the transport of things in crystals. So I guess that's where 153 begins. What's the title of this chapter? Long-range translational diffusion. So that's our first mode in our paper. Like he talks about right at the beginning, he says, like, I'm sorry that this thing is so involved, but we have seen this quasi-elastic thing from Nichols, and also, I guess I mentioned it. So this is the long-range translational, this e to the minus q squared. That's directly from that B book. That's the long-range translation of water through the membrane. All right, so what he means by long-range translation is, if you go back to his cartoon, so he has these cluster regions, like holes in the membrane, which you could maybe see in the micrograph if you want to have imagination. And then within that, there's going to be like 20 water atoms in there. And those are translating, that's your first relaxation time. This is important because a group did exactly the same measurement as he did before he did it. And that's all that they saw. They just saw that and they said, like, this membrane doesn't work, even though it's commercially used. So he said, like, the water's just zipping right through this puppy, there's no selection, there's no transport restriction. Then what he did is he didn't just soak the membrane in water. First, he went through this thing and he said, well, like the polymer is contributing to this, that could be why. So he measured the polymer alone, he separated that part out. And then he said, well, there's something about there's too much of this whole water in there. And there's also the thing is soaked in water, so it's like the surface water, just bulk surface water. So their measurement was kind of bogus. I mean, they were measuring something, but they were just measuring things that has no consequence. The water's moving back and forth. It's Brownian motion within a hole. So nothing, it's not the transport part. So what he did was he soaked the water, he reproduced their measurement, and they took the membranes and he put them into humid environments of different amounts. So he could soak different amount of water into it. So you get like kind of the surface coating of the water and get the transport of that surface coating, and then so he did that in a separate paper. That's in a paper that I just put up there, water uptake rate, this thing. So he's got, this is his paper too. It's the same guy, Foglia. And then he's doing neutron reflectivity, where he takes the films, it's the same stuff, right? It's this trifunctional chloride and the diamine. And he does this is in hexane, that's in water. It's this nylon rope trick, except he's got a fancy rope coming out. The nylon rope is 612. So 6 carbons, 12. That's the normal nylon. And then, so basically he's using an aromatic to make it kind of a stiffer. Anyway, so it's basically the same thing as nylon rope trick though, except at a surface, and he doesn't pull the rope out, he just leaves it there. So it's 100 nanometer rope that's sitting at the surface between the water and the hexane. Then he does reflectivity off that, shoots a neutron beam and an X-ray beam off that. From that, he can get the profile. This is a reflectivity curve. So that's the intensity that came in by knot. So when you get to the critical angle, the beam that came in bounces right off. So below, I think it's 0.2 degrees on silicon. So it's a grazing incidence. So you get full intensity out. Take that intensity, and as you go up, you get beyond the critical angle, and you start to probe the surface. So the ratio of the two gives you this reflectivity. The intensity you're measuring at some angle. It's a specular measurement, so incoming and outgoing to the same angle. There's also off specular that tells you something about the structure. The specular just gives you the Z direction profile of the density of what's in there. And if you're looking at this film, that's important, because if you use neutrons, you can see the hydrogen density across the film. So you can say like where everything is. And then he does that as a function of like soaking it or hydrating it with slowly with humidity in this paper. So this is the previous paper to this Nature paper. Now you can see people get a little bit involved in this subject. I mean, it's basically, so someone came along, they were doing nylon rope trick. Why not do that with like a piece of fabric or something? Oh, that's a pretty thin layer. I wonder if it transports. Oh, look, you can use it for reverse osmosis, and that becomes an industry. So that works great. Then how do you make it better? Well, you can play around with the chemistry, put these aromatic things, make it stronger. But then after that, you have to start to understand like what's going on, like how does this thing be a barrier film when all it is a nylon rope trick? Like you didn't do any special casting, you didn't do anything. You just poured in water and cyclohexane, and this thing suddenly appears on its own. It's like a miracle, but it isn't a miracle. Something happened, right? So basically that's how this can lead into this huge thing of a bunch of neutron scattering stuff. So it's kind of a twisted tale. On the other hand, there's a ton of money being exchanging hands for something. I mean, if you're selling 100 micron film of nylon, which is cheap, for what, like, thousands of dollars. So like it's pure profit. This is a money printing machine, right? The input cost of this is zero. And the output gain is like billions of dollars. So this is just like, if you want to be a venture capital, like this is the perfect thing, right? So there's a huge market. No one knows how to do it. It's all trade secret. And you just keep the secret, shoot anybody that messes around with you. And like, basically, this is forever money because everyone needs water to drink. and everyone lives near an ocean. I mean, most people live near an ocean, right? So they can't drink it, but they could if you give them your magic film, and they'll pay anything for it. So, I mean, that's why people want this thing, so you can kind of see how this fit together, starting with a stupid nylon rope trick, but which was I mean, I think that was basically invented by Carruthers, the guy who killed himself, from DuPont. Like all the condensation polymers came from Carruthers. He invented the whole slurry of them, all the polyesters, and then all these amides and things, nylon and everything. He's a genius, but basically also had this problem, like whatever. So anyway, so anyway, so they that's what they do. They do these reflectivity measurements in this paper. It's kind of in this, they end up with a profile like scattering density. So density as a function of z is in normal direction, and they can see the water uptake. So you can get a profile of what's going on with the water. So that's where he's coming from when he goes to this thing and he says like the water uptake, and it's going to go because of the steps that happen in this. I know I have these pores. I know there's something going on with this. So I want to go in with quasi-elastic neutron and break it into all the actual pieces of what's going on in this thing, the different diffusion transport mechanisms that are in this. So let's see. Yeah, there's a lot of, that's kind of what's going on here, I guess. Let's see. So we got to pick through this chart then after that. Right. So there's a lot in here. He goes through a lot of different analyses and like breaking this into the bulk transport term. And so first he does the polyamide, and these are the things he talks about, basically the rotation of that difunctional ring. And the other ring's kind of fixed because it's tied three ways. But he's got like the spinning relaxation of that, and he discusses that ad nauseum. This is the gamma from the Lorentzian function, right, wherever that is. So that's that gamma, which is the half width. So you can think of that as how broad that. So there's a sharp peak, and then the broad thing behind it. There's also a background, like an incoherent background. So there's three parts, right? So, and then that the Lorentzian can be made up of different components, but he can pick different energy windows with his backscatter and time of flight thing, and he's scanning energy anyway. So basically, he can pick apart that Lorentzian broad peak and get this gamma for all the different modes of motion that are happening in this thing, because he's got like these are like literally billion-dollar instruments. These things he's using, these backscatter, they're huge room size, like gigantic machines, for the either nuclear reactor in his case or a spallation source connected to him. So big megabutts, and there's like only a couple people that can figure out how to use it. It's kind of an interesting little niche. The whole field he's in is kind of a niche, and then the instrument he's using is also another niche. There's two niche things kind of meeting each other to make this Nature paper that got published, but it's like something that nobody can read. Like you have to, in order to read it, you have to read B's book. You have to kind of figure out what's going on in both fields, The fields go back, like the water. So this, also the general topic of water, like how water, the dynamics of water, like structure of water near hydrophobic surfaces, 1998, also, so this is also the French, kind of near Grenoble, near the neutron place. Also, he talks about neutron stuff in here too, but this is for biological. This guy's doing X-ray diffraction of water at different temperatures, at interfaces and things, and seeing how the structure of it changes, and how there's this like cage structure it forms, and then there's these 10 nanometer clusters of water that are moving around together, and they form a structure, and even in super cooled water. He cites this paper, and that's why I bring this up. And then at the end, he talks about quasi-elastic neutron scattering measurements on these things down here, I guess somewhere. But basically, like this is energy versus something. Anyway, this paper is kind of interesting to look at too, but it shows you, and he's citing other papers. So basically it goes back to the 1970s or before, like this dynamics of water. So just water alone, because it's the basis of life. So all life has water, and motion of water is important. then like even in these almost in all the, it's the cheapest solvent, right? So it's the cheapest thing actually on earth next to sand. In fact, I think water and sand, I think water's cheaper than sand, right? It's like water, sand, air. There's like some things that are free, right? So basically water is used, it's like coolant material, everything, right? So the dynamics of water, people have some interest in. I mean, anyway, so even just water in general, like structure of water, or whatever. So anyway, this is all just studying the this is the EISF, is the elastic incoherent structure factor. So this is basically the structure factor versus Q for the, this is basically the scattering, right? This is just the scattering versus Q versus 1 over the angle versus the 1 over the angle for this thing. So, or versus the angle. So this is just like a diffraction pattern kind of EISF. And then he's got, so that's the structure factor. So this is getting this dynamic thing versus Q squared, which should give you the dynamic width should give you the diffusion coefficient. He gives that equation somewhere here. The gamma is related to the diffusion coefficient because it's the time, it's a relaxation time. So that when the relaxation, and if you use the Einstein-Stokes, it's going to be relaxation. The diffusion coefficient is kT over the viscosity. The viscosity is somewhere there's a time in there. Diffusion coefficient is the time times the mean square displacement is a time times the diffusion coefficient. He measures the mean square displacement too, like this right here, mean square displacement versus temperature. So if that's a straight line in temperature, it's because mean square displacement is the diffusion coefficient times time, and then the diffusion coefficient is kT over 6 pi, the hydrodynamic radius in the viscosity. So basically this thing should be proportional to temperature if it's following Brownian motion. So that's what the dashed line is here. Dashed line is for basically Brownian motion. And then for his hydrated polyamide hydrated with D2O, you can't see that. So that one would be just the hydrogens in the polyamide, not the water. And the other one is the dry polyamide. So dry, when it's soaked in water, how the D2O affects the motion. And the last one is a combination of those two plus water moving through it. So the non-Fickian part, the non-diffusive part, that's shown by the deviation from the dashed line. And when you get to really low temperatures, it's just diffusive, Brownian motion, right? So I think he calls it Fickian here. But so and then these things are the other, it's not really clear like which axis goes with which, but these other things are the scattering function, basically that versus temperature at fixed Q values. And that's showing that when it's hydrated polyacrylamide or hydrated with D2O, where you only, so this one you only see the polymer hydrogens structure. And in this one you see the polymer hydrogen and the water structure. So it shifts, it's different. So this, you can see, so he's kind of demonstrating that you can see the water isolated from the polyamide if you measure the polyamide alone and then measure the two things together. It's a mess. It's absolutely a mess. Like if you read this, it's like over and over, like you have to read this paper 5 times and then you still don't really know what's going on, I think. But basically, if you do that, you can kind of get a feel for how, where things are going here. Anyway, the more you read it, the more it does seem to make some sense. Like it's kind of worth the effort that he put into it and everything. Anyway, so this is all the components of the things. Let me just read through this. Schematic of the experimental result: diffusive modes of water confined within the polyacrylamide membranes, namely localized diffusion. Okay, so this is A. So localized diffusion is just water diffusing. That's D local. So this is versus 1 over T. So if that's a straight line, let's see. If it's a straight line and this is log, then that's an activated process, I guess is what he's saying here. That's the Arrhenius. This is an Arrhenius plot. Like that thing is 1 over T. The slope is the energy. even though the Brownian motion one's supposed to be proportional to T. But so this is an activated diffusion coefficient, that straight line, which I think he explains in the paper. And then the other, so the other guys, that's the localized diffusion booster. Translational diffusion. So he shows the picture of the translation. That's like Brownian motion through the network of polyacrylamide clusters. This translational one. So this is, and then there's a tau here for these things too. So the taus for these guys, so some of the taus are going with the one technique, the nanosecond, the other with the picosecond. So this is backscatter and time of flight. So there's two scales for the things, and then these couple, so the symbols match up. So the localized, this is localized, so the relaxation time should be an Arrhenius behavior. So it should be log of that versus this. This guy's not supposed to be Arrhenius, I don't think, but anyway, he shows it's Arrhenius. So anyway, so that guy, the square ones are the translation. So the relaxation time for translation is faster than the relaxation time for the LRs, the TRs, the hopping one. So the hopping one is slower than the translation one. Translation one is faster than this hopping thing. The hopping thing has a length associated with it too, this length of the hop, and the length of the hop doesn't change across this thing. The blue things are, so the red things are, let's see. So bulk water is black, immersed PA polyacrylic is blue, and red, and what is it again?
No, the red one is hydrated.
Red one is hydrated PA.
In the middle, the blue.
Oh, here, okay, red is hydrated PA, good, thanks. And the other one's immersed PA. All right, so hydrated means he just puts a humidity onto it, and immersed means he dunks it in a bucket of water. So immersed is what was done before. So he shows the immersed data. These triangle things, I think, are the previous measurements. So he's got all these things, and the previous people did the same measurement, and they got those triangle things, right? So they're close to the bulk water. Actually, the bulk water is the black. He says their measurements are like bulk water, basically, and that was their conclusion, was that the transport through the membrane is bulk water. So it's basically, there's no separation in it, even though it works. You know, that they said it didn't work by this measurement. And he's kind of resolved that it can be picked into the pieces. All right, so is that business. Then what else is in this thing here? Sounds like you guys know more than I do about this. I get confused, but long-range diffusion, tortuous red arrow. Then B, translational water diffusion map showing the diffusion coefficient as well as bulk water diffusion. Present data, water dynamics with by vapor hydration, time of flight, and backscatter, immersed in liquid water, time of flight. So they only did one measurement, the immersion people. They didn't do a backscatter. And then previous Quinn's measurement of water and PA membrane. That's the triangle things. So he did the immersion because he was reproducing what they did, the time of flight. So he did the same measurement that they did. So that's his squares. And that matches kind of what they did, but it also perfectly matches bulk water. It's like there's no difference between these little circles, cluster thing, and bulk water. And there's no difference between that and their thing, even though they may have drawn some distinction between the slight difference, right? And then he says there's this fast diffusion of the translation, and then the local. I don't remember what local is. Oh, local is within that cluster thing. Then what are these things? These are bulk water. Local's confined motion, I guess, within the cluster. This is bulk water, and then this is his translational diffusion that he gets. He sorts that out he does that by hydration. So he does hydration, he gets translation, and he gets this this hopping mechanism. So he gets those two in his hydration measurement. He gets these in the, anyway, so he picks the thing apart that way. And he's comparing, these are simulations here. So simulations come out in the middle. It's like the simulations don't seem to really say much. And also, if you really look at this, I see there's a star there, but the symbols if you like some of these symbols, all right, so where is that, like there's a hollow star here, right? So where is that? Like there's no, do you see a hollow star here? See this symbol, hollow star? Where is that down here? There's no hollow star. So some of the things, and then like if you try to find the solid star, like it could be buried in here, I guess, or maybe the hollow star's in there. I don't know, but the hollow star doesn't have a definition. This thing's like a bunch of different symbols piled on top. You can't tell what's. So anyway, he's got all the data in the universe in this plot, if you look at it, but it's so confusing to, you know, the lines, and he's kind of drawn it out pretty well, but basically it's confusing. And then, yeah, then he has the taus here. So let's see. Fission fraction mobile, hydrated, blah, 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 DS. And then he's got this DSE trace to see the crystallization of water near bulk temperature. So he's showing, he's going through 273 here, you know, so he's going through melting point of water in all these measurements. So he's, which brings, like, makes you wonder what's going on. But, and if you look at the 273, I don't know if he's got straight temperature here, but if you look at 273, something happens there, you know. But he's saying that it's super cooled water. It's not ice water when he does this. And I guess he has some evidence for that, you know, but maybe he just does a diffraction pattern on it, but I don't know if he does that, but anyway, so anyway, there's some questions I would have just offhand, but and maybe the stupid questions, you know, like, does the stuff freeze when you go through 0 degrees C? Because if you look back at the plots, it might be a stupid question, but like 273 is there, that's where some transition happens. Just look at it coarsely, you know. It kind of seems like something happens at 273 in all these plots, and he doesn't seem to be bothered by that. And temperature 273, it's where his peak is and all these things, and 273 is kind of where things deviate. I don't know. Anyway, so I'm not sure that means anything. I think they have that sorted out. That's probably the first thing anybody looked at. But anyway, so this thing has some just broad questions, like what is the jump diffusion mode? I think it asks that somewhere, and I put some links to that here. Fixed window scan, TMS, water uptake rate, heterogeneity of polyacryla. That's that B book. There's that membrane book that I was talking before. There's a talk here from Oak Ridge on, I think it's from Oak Ridge on this quasi-elastic neutron scattering, which might be of some help to flip through if you want. Like here he shows there's a background. So you do the measurement, it looks like that. There's a background, incoherent background. There's an elastic peak. This is against energy or frequency at the bottom. And there's this Lorentzian thing at the bottom of it, which is kind of the dynamic stuff. And then he gets this del, which is omega and the other thing. And then he talks about backscatter and time of flight and compares it to, in this paper, you can kind of see how that works. And they're big machines that cost tons of money. The whole thing costs $1 billion, like the whole setup. And then this is I think this is, I'm not sure what this is. Oh, that's the basis. So that thing sticks out to get the energy resolution, sticks out of the building. So since they dump so much money in it, you can see that they're kind of interested in using it too. So in problems that are of importance to people. So the separation membrane thing is probably one of the major ones. So that would kind of show you why it's in nature. Like there's a ton of money invested, and then like anyway, so what's the questions here? Let's see. Our hypothesis. So he's got these hypotheses, right, for what the transport is in these membranes. So his hypothesis is it diffuses through the network, bulk polymer matrix, and there's aggregate pores. That's a circle thing with the water. And then resolve with the judicious choice of blah, 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 what he did to distinguish between these transport mechanisms. And then he says other physical pictures. So what are the alternatives to that? So interfacial and bulk water diffusions, that's like a common thing in transport, right? So the water So you could separate just by having one component absorbs to the walls. So the amide is hydrophilic, so the water sucks up to the walls. When it's on the wall, the transport is going to be much slower than in the bulk. And then there's going to be, so depending on the pore size, so if the pores get to nano size, they can be all wall because there's a molecular size and then there's absorbed to the surface. And if the pore gets smaller than the molecular size, you have something like nuds and transport, like the things that are kind of all wall. So then the transport gets really slow. Right, so you could talk about that interfacial versus bulk transport. That's one model that you could use, And then subdiffusive dynamics. So within the dense polymer membrane. So if it's a solid membrane, you might not see Brownian motion. It might not be a random process, whatever. So it's subdiffusive. So if the pores are straight through, it would be super diffusive or ballistic. And if the pores are going the opposite, or if it has to like go through a tortuous path, so that tortuous path diffusion is shown to be subdiffusive because it's blocked. So if you have like polyethylene with crystals, and it has to go around the crystals and through the amorphous to get through, like if you get CO2 through a polyethylene film, like cornflakes bags. So you don't want CO2 to get in, it'll make your cornflakes soggy or something. So you have the crystals are aligned. When you blow mold the film, you make the crystals align like that, not like that. If they're like that, the water goes straight through the cornflakes. If it's like that, the water gets stuck in this tortuous path. So it's a subdiffusive motion. So like that, it could be ballistic even. So it could be faster, super diffusive. Right. So that's the kind of thing he's talking about. Subdiffusive means he's putting impediments to the water transporting through. Impossible spatio-temporal coupling with multi-scale relaxation processes within the polymer network. So that means like you have no idea what's going on. So it's something to do with the structure. There's a combination between the structure and the time. He doesn't say what that connection is. He just says, so he's using a lot of words, but he just says like there's a mess. That's what he's saying there, right? Spatio-temporal coupling. So somehow the structure and the motion are coupled together. And multi-scale relaxation. So there's all these different things going on. Just saying it's a garbage can of things going on, and we'll never know. I guess it's the last model. Basically, that's a model that he's kind of picking apart here, I guess. Anyway, I thought it was good to kind of look at that and explain each of the four possible whatever. Water diffusion, some of it, you could look up some of that or fish through, do whatever you can do. And then describes what is a fixed window scan. I think if you can explain that, you kind of are well on the road to knowing what this quasi-elastic neutron thing is. Because he says like, here's this fixed window scan. It never says like, what is it? So basically, it's got to do with these choppers and kind of you can select the energy window for the absorption. So you're doing scattering and energy at the same time. So you get this multi-dimensional data set out of it. If you can figure out what a fixed window is, then you kind of can tell what everything is that's going on, I think. So or at least you're on the road to figuring it out. And that Q dependence, explain that diffusive and local motions can be discriminated by the Q dependence or independence, respectively the characteristic maximum. So that's in the second part of this picture. So he shows the first part here, and he's got this maximum, right? So and these are at different Qs. So there's a Q dependence when you have the hydrated polyacrylamide, when it's hydrated, but you can't see the water. So this is just the polymer motion. It's not Q dependent. So he's saying that diffusive and local motion. So local motions would be not moving in Q. Dependence or independence. So in other words, the polymer is fixed, and it's not, the motion is not Q dependent. Anyway, the experimental evidence is that that's true. And the water's moving, so it shifts with Q. So it shifts with Q because there's like a size scale of the hopping. It's a hop mechanism, I think. So he's got a distance scale associated with the hopping. So it's going to, I think that's kind of what he's talking about. Anyway, you can figure out what he's saying there. But these rules demonstrate that the data from PA membranes hydrated with water, the information from water diffusion with those from pH hydrated with D2O isolate the polymer dynamics in the hydrated state, printing their decoupling and the scattering data. So that's good. Explain equations 2 and 3, how are LA and SA motions decoupled. So decoupled because he uses the backscatter and the time of flight. They're measuring at different time scales. So you can decouple large amplitude and small amplitude motions. And equations 2 and 3. So he's got this thing, the del thing is just that exponential decay function thing, whatever that is. This thing, E, the del is just this bulk transport with a mean free path of the atoms, like a diffusive thing. And then the 2 and 3, and then the others are the small amplitude and large amplitude relaxation motions, which he talks about in here, like that they're, I think that's just an observation. There's large and small magnitude motions in the thing. So he separates those into two things. And then the del part's out front here, and the two things are both Lorentzian terms. So he's going to separate those two by using the two instruments, the time of flight and the backscatter machines. Again, like if you can kind of answer that, it gives you a better idea of what he's talking about. And the jump diffusion model, that's all over the place. If you Google that, you will definitely find it. It's not just to do with this. It's like a whole mechanism of how you understand transport on a molecular scale. Like on zooming out, you see the dust particles moving around, Brownian motion. But if you zoom in and it's going through a material, it's going to go by this jump. No matter what the material is, it's going to be like jumps. It's Brownian motion, but it's taking place in steps of a fixed length, and there's a frequency to that. There's a tau, a relaxation time associated with that. Anyway, here there's some link here to, I think, water uptake, fixed window scan. You can just Google it, I think. I don't have a link to that, but basically that's kind of their bulk water and for water, hydrated membrane, suspension of water over T, explain why this occurs. That's a Arrhenius plot. So anything that's log of something versus 1 over T, you're getting an energy from the slope. I mean, you should recognize that immediately. That's a plot you'll see over and over again. Something log 1 over T, slope is the energy or the enthalpy. And it's like the energy of the activation energy. It's the slope of that thing. So you should recognize that immediately. That should be your friendly point in these complex papers. You find something log versus 1 over T, I know what that is. They'll get an energy. It's an energy of something happening. And then you say, like, what is happening? That's and it's, if it's a straight line, it confirms that it's a thermally activated process. Right. So these are touch points where you can take anything that's super complicated and they're going to always go back to that. And that's a simple thing, the Arrhenius thing. Any dynamics is going to have Arrhenius in it somewhere. And somewhere it's going to have the Einstein-Stokes thing. And so you can kind of find those, weed through all the stuff and then find those things. And then now you also have this Lorentzian thing. That's another friendly point, kind of, or less friendly. But you can go through this book, for instance. It's completely unreadable. Just look for the places where you see the Lorentz function, and then you kind of know that, and you can backtrack through the book, like what is he talking about? Because that's like a Maxwell relaxation thing. That's got some tau to it. You kind of have a rough idea of what's going on, and no matter how complicated the thing is, if he uses that, that's just simple. That's one relaxation time. And the thing's just going on like that. Anyway, why don't we quit there? So again, I kind of apologize for putting this paper on you because it's like pretty complicated. And the idea of the membranes was to get something simple, and then someone said, like, this is, it's in Science, it's a top paper in membranes right now or something.